All right, let's jump right into this explainer. If you've ever wondered how your smart speaker actually decodes your voice or how a search engine knows exactly what you mean even when you misspell it, well, you're in the right place. Today, we're diving deep into the basics of natural language processing. So how do machines actually understand us? I mean, from talking to our phones to barking orders at our smart homes, what is literally happening behind the scenes when a machine is listening? We take it for granted every single day, right? But the gap between our messy, organic human speech and rigid computer logic, it's massive. Just look at the timeline of NLP evolution. It's wild. In just a few short years, we saw some massive game-changing leaps. In 2011 alone, IBM's Watson wins Jeopardy and Siri hits the iPhone. Then, boom, 2014, Skype gives us real-time translation. And by 2018, Google Assistant is literally making actual phone call appointments for us. But here's the real takeaway. These tools are everywhere, absolutely, but none of them work perfectly yet. They constantly need empirical methods to keep improving. So, to really grasp this, we're going to break this explainer down into 4 key areas. First, the rise of NLP. Second, the layers of linguistics. Third, the massive challenge of ambiguity. And finally, how we evaluate AI language models. All right, kicking things off with Section 1, the rise of NLP, moving from natural language to structured information. The fundamental goal of NLP is basically bridging 2 completely different universes. On one hand, you've got the messy, unpredictable, continuous flow of human speech. And on the other, you've got the crisp, interlocking gears of computer algorithms. NLP is the whole process of taking that chaotic natural language and transforming it into structured, predictable information that those mechanical algorithms can actually process. Moving right along to Section 2, the layers of linguistics, where we decode the actual structure of human communication. To a computer, human communication has to be unpacked layer by layer, kind of like navigating concentric circles. It starts right at the center with raw speech sounds, your phonetics and phonology, and ripples all the way out through syntax and semantics. Eventually, it reaches pragmatics on the outer rim. And pragmatics is absolutely vital because that is how we actually accomplish real-world goals with our words. To anchor this in reality, let's look at the token. This is literally the smallest text unit an algorithm looks at in NLP. If you feed a machine the sentence "cats ran," period, it doesn't just absorb a continuous thought like we do. It chops it up into individual tokens, so the separate words, cats and ran, and yep, even the period at the end. To a computer, a punctuation mark is just another token that needs to be processed. Going slightly deeper into the weeds, we have morphemes, these senseful components of words. This is where we help the machine distill fully inflected words back to their raw, dictionary stem forms to find their core meaning. For example, stripping the S off cats down to just cat, or reverting ran back to run. Doing this prevents the algorithm from getting confused and treating pluralized or past tense words as brand new, totally unrecognized concepts. But just when you think language can be perfectly categorized into neat little tokens and stems, we hit Section 3. The challenge of ambiguity, or the chaos of implied context. See, word sense ambiguity is a massive, massive hurdle for computers. Imagine a cartoon where a literal metal desk fan says, "I'm a huge metal fan." As humans, we instantly get the joke, right? But without general world knowledge, a machine is totally stuck. It has absolutely no clue if we mean heavy metal music or a literal spinning fan made out of metal. And it gets trickier because domain dependency and slang can completely derail a literal interpretation. Take the phrase, "this is shit." Obviously, highly negative, right? But throw in one tiny word, the word "the," making it "this is the shit," and suddenly you've completely reversed the sentiment to being highly positive. A machine just reading a standard dictionary would completely miss that cultural nuance. It's wild. And check this out. Listen to how simply shifting my verbal emphasis changes the entire meaning of one single sentence. Watch. I never said she stole my money. 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 The text tokens for all of those are exactly identical, but the implied pragmatics, they change entirely. Maybe someone else said it, maybe she just borrowed it, or maybe it wasn't my money to begin with. It's a logistical nightmare for a computer. Because perfection is clearly impossible with all this ambiguity running around, let's dive into our final section, evaluating AI language models and how we navigate this mess empirically. To teach the machine anything at all, we have to rely on text corpora. These are massive collections of real-world texts that have been mapped out by human experts with known properties and ground truth annotations. Think of it as a giant, highly detailed answer key. It gives the algorithms a reliable baseline for comparison so they know what actual human understanding is supposed to look like. Now, when we run classification tasks, say asking an AI to catch spam emails, we map its guesses into this grid you see here. We're looking at true positives, true negatives, and false negatives. It's essentially a scorecard that shows us exactly where the machine correctly caught a spam email and where it, hallucinated and flagged an important email from your boss by mistake. From that grid, we calculate two incredibly important metrics: precision and recall. We use precision to measure exactness. So out of every email the machine flagged as spam, how many actually were? On the flip side, recall acts as our safety net. We ask, are we letting too many actual spam emails slip through the cracks? It's a constant, tricky balancing act to get both numbers where we want them. But what if we're dealing with numeric predictions, like having an AI guess a rating from 1 to 10? For that, we use mean absolute error, or MAE, to find the standard deviation. But sometimes, massive outliers are disastrous for a model. In those specific cases, we switch gears to mean squared error, or MSE. By squaring the math, we basically drop an anvil on those massive errors, penalizing them heavily and forcing the AI to play it way safer. Ultimately, teaching machines language isn't really about achieving perfect comprehension. It's about measurable, iterative improvement using these empirical methods. And honestly, that leaves us with one incredibly provocative question to wrap up this explainer. If human language is such a chaotic web of implied context, sarcasm, and endless ambiguity, will machines ever truly understand us, or are they just mathematically predicting our next word really, really well? Think about that the next time you ask your smart speaker for a favor. Thanks for joining me on this explainer, and keep questioning the algorithms around you.